So when EM is greater than EL. So as I said just now, EL is the initial state, EM is the final state. Okay, this is one is the ground state, another one is excited state. We are going to find out the transition probability between these two states. How to find the transition probability? Just squaring the amplitude. You just square the amplitude. So this is first order correction. Can you remember in time dependent perturbation theory? This is first order correction. Just to square the amplitude, that will give you the transition probability between two states. So just to square it. So we have A1M is given by this. Complex conjugate of this will be this. You are going to take the complex conjugate. What is the complex conjugate of H? H is an operator. So you have to go only with a H dagger. H is an operator. So H dagger. H equals H dagger. So we are going to replace with both the things. And here e power I is here, e power minus I is here. Okay. Now you are going to multiply these two. When you are going to multiply, you will have I into I squared minus 1, already one minus is that. So this will become plus. So here plus. The square of the perturbing field divided by H bar, and H bar will give you H bar squared. Now we are going to multiply these space factor term. So I have multiplied. So here this is first term and this will be your second term. As usual, in the last lecture we were able to see this. Can you remember? Similar to this. So we are going to multiply this factor to this first one and this factor to this second one. So we are going to multiply this factor to this and this term to this. So we will have 4 terms. Okay, we are going to multiply. So we have 4 terms now. This multiplied by this will give you 1. Similarly, this term multiplied by this and this term multiplied by this and this term multiplied by this, we will have the numerator expressions. Is it okay? We have 1 plus 1 is 2. I am going to take these two terms, that minus sign out. So that will give me this. We have already seen earlier the same technique. And multiply and divide by 2. You are going to multiply and divide by 2. So this will have, this will just guess, this will be your cos term. So this will be your cos term. So we are going to replace this term into cos term. So we are going to replace this term into cos term. So 2 minus 2 cos theta, that is cos omega ml minus omega t naught divided by omega ml minus omega whole square. Okay, just bring 2 out. So that will give you 1 minus cos theta by theta square. 1 minus cos theta will be 2 sin square theta by 2. So we have 2 sin square theta by 2. Okay, so 2 2's are 4 now. You just bring 4 here. Okay, so remaining term let it be. So we will have final answer will be exactly this one. I have written the same equation and the final answer will be your 2 2's are 4. This will be your final answer. This is for the absorption. So this is your final answer. When EM is greater than EL, we have the expression for transition probability. The expression goes like this. Exactly equation 7.62. Any doubt? So this is for the absorption. Similarly, you can go for the emission. So this is for the emission equation. Similar one. Okay. This is for the absorption. This is for the emission. Just look at the equation. This minus is here. Here it is plus. Okay. These two things are very, very important equations as far as this harmonic perturbation is concerned. So one is for absorption. We are going to have separate graph, and we are going to have a separate graph for the emission too. Okay. So this is for absorption graph. Okay. And we discussed already this graph earlier, and we are going to plot this phase factor with omega ml minus omega. So as we discussed earlier, and this will have more contribution only exactly at the center of peak. Okay, center of peak. So we know already. That means when omega tends to omega ml, okay, when it comes towards this side, only then we can have a very good contribution. Okay, the contribution is more effective only at the around central peak. So this is your central peak, and we discussed yesterday in the last class. This is exactly resembles with the optics interference pattern. In interference pattern also we have the more effect only at the central peak. Either side will be very, very less, 1%. Okay, so similar to that. What is the height? Height is nothing but your T naught squared by 4. Yesterday we discussed. In the last lecture we discussed this is height will be T naught squared by 4. What of the width? Width is directly proportional to 1 by T naught. What of the area? Multiply these two. Height multiplied by area. So 1 is T naught squared multiplied by 1 by T naught will give you your T naught. So our area is directly proportional to T naught. So area means amplitude square. Amplitude square is nothing but your transition probability. Okay, amplitude square is nothing but transition probability. Commands here, amplitude square is nothing but transition probability. So area is nothing but your transition probability. The transition probability is occur more only central around the peak. So this is what I want to say. One. And second idea is, and we know that it goes to the 0 in the x-axis with this condition, omega ml minus omega t naught by 2 equals n pi. Yesterday we discussed the same thing. Sin n pi equal to 0. So this condition only, this will become 0. So omega ml minus omega equals 2 pi by t naught. Just cross multiply, you will have this one. And suppose for the first one, for the first condition, when n equals 1, you just substitute when n equals 1, you will get this expression. When n equals 2, you will get this expression. When n equals 3, you will get this expression. When omega ml minus omega, it's a difference. If difference is very large, it means omega is away from omega ml. See, I repeat, omega ml minus omega is a difference. This is in the x-axis. If difference is very large, that means omega is too far away from omega ml. It means that you have less amplitude. See, look at the amplitude is very high, amplitude is very low. See, it is low. Almost its amplitude 0. When omega ml minus omega, the difference is very large. If omega goes too far away from omega ml, the contribution is very less. If omega approaches omega ml, the contribution is very high. So this is what I want to say. Okay. So this is about the plot for absorption graph. Similarly, you can have the plot for emission graph. So we have both the equations. So absorption and emission. Only difference is you have omega ml plus omega equals 2 pi by t naught. There it is minus. Here it is plus. Almost the same contribution. If omega ml plus omega, we are going to have omega equals minus omega ml. Okay. That is if it is too far away. That means omega is too far away from the value of omega ml, then will be very less contribution. If omega equals minus omega ml, nearly it's equal to 0, then the contribution will be more. Okay, this is for the emission. So as I said, there are two conditions, omega equals omega ml and omega equals minus omega ml. These two conditions are called resonant conditions, at which the main contribution will occur. Okay, one is for absorption, another one is for emission. So when omega equals omega ml, so it means that Em equals El plus h bar omega, Em minus El equal to h bar omega, we can get the maximum value. This process is known as absorption. So here the effect of perturbation transfers the energy to the system. So you have an electromagnetic field and you have an atom. So there will be a transfer of energy from electromagnetic field to the system, because the system absorbs the energy from external perturbation field. Okay, so this is absorption. But here, when omega ml equals minus omega, the condition is Em equals El minus h bar omega. It implies that the effect of perturbation is to receive the energy from the system. Now the system will give the energy to the perturbing field. In the first case, perturbing field will give the energy to the system, and in second case, the system will give the energy to the perturbing field. And this energy is reduced by h bar omega, because reduced by minus h bar omega, it gains. Here it reduces. This process is known as emission. That is the reason that equation 7.6 to 7.63 are very important. This is for absorption, this is for emission. When omega ml equals omega, the equation 7.62 becomes, okay, suppose if you are going for omega ml equals omega, suppose then we can say that when theta is very small, sin theta becomes theta. So if omega just nearer to omega ml, then we can write sine theta which is equal to theta. So we can write the angle part alone, which is nothing but omega ml minus omega whole square t naught square by 4, because square is there, okay, divided by this factor, and this one is will cancel. So we have t naught square by 4, this 4 and this 4 will get cancelled. We have this condition for absorption when theta is very very small, that is omega ml is equal to omega. Similarly, when we go for omega ml equals minus omega, the same equation, we are able to get the same equation. So this is for the stimulated emission and this is for the absorption. So as I said, this is a two-level system. We have only ground state and the excited state. So we have two-level system. This is a system, automation system, and you have external perturbation, which is nothing but your perturbing field. So the system absorbs the energy and it goes to the excited state. So this is called absorption. The initial state is nothing but EL. Final state is nothing but EM. Okay, so EM equals EL plus h bar omega. It gains 1 h bar omega and goes to the excited state. So this is the process for absorption. And here, in this case, the population will be more in the excited state. So now these electrons will be trapped due to the external field, and it will come to the ground state by emitting some radiations. Whatever it has gained, it has to emit, and it will come to the ground state. Okay, so stimulated emission. So now you have initial state is EL, your final state will be EM. So EM equals EL minus h bar omega. Here it gains 1 h bar omega, here it loses 1 h bar omega. This is for absorption and this is for stimulated emission of a photon of energy 1 h bar omega. Is it okay? So as I said, this is for absorption and this is for emission. These two conditions cannot be satisfied at the same time. Okay, very important. Either the first condition or the second condition. Either it can gain or it can lose, not at the same time. So in constant perturbation, in the earlier topic, the system is neither removed from the system or it is transferred to the system. So here energy is constant in constant perturbation. But here in the case of harmonic perturbation system, the system absorbs the photon of energy h bar omega due to the perturbing field and it emits the energy of a photon. So here only, as I said, you have only two parts. One is perturbing field, another one is system, which is nothing but an atom. So it absorbs energy from the external field, perturbing field, one, the first condition, and the second one will be it will lose or it will give the energy to the energy perturbing field, whatever it has gained. So this is called emission and that one is called absorption. Okay. So now we will try to solve one problem which is a very important problem as far as your examination is concerned. So it may appear in CSR examinations too. Just we will try to solve one problem. Okay, so this is for the, it is related to the perturbing field. A particle of mass m having a charge E contained a 3D box, and we studied already about 1D, one dimensional. So that particle moves in one dimension, we have already studied. Now the particle is in the 3D box of side is given as 2a and is acted by an electric field. So external perturbation is something about your electric field. So you have an electric field, you are going to apply the electric field and the electron is inside the box, it is trapped inside the box. The electric field term is given as exactly like this. E equals E naught e power minus alpha t as t is greater than 0. Now the electric field is applied only in the x direction. So there will be no electric field in the y direction, z direction. This is cubical box, 3-dimensional box. So x axis, y axis, z axis. As it is given as electric field is applied only in the x direction, it's not in the y direction, not in the z direction. We are going to calculate the probability that a charged particle in the ground state at t equal to 0 is excited to the first excited state by the time t equals infinity. So our aim is to find out transition probability. Our aim is to find out. So we have to use the square of the amplitude for the first order correction from the time dependent perturbation theory. Okay, so that's the idea. Now, so for the cubical box, we know that the energy eigenvalue is given by this expression and the wave function is given by this expression, we know already. We studied for one dimensional problem En equals n squared pi squared h bar squared divided by 8a 8m a squared. Can you remember? For one dimensional box. So we already studied this one. But here it is given as 3D box. So we have to go with nx squared plus ny squared plus nz squared. So instead of that I have written as j squared plus k squared plus l squared, all quantum numbers. J, k, l is nothing but 1, 2, 3. But your wave function is given as 1 by root a cube. This is for the x direction, this is for the y direction, this is for the z direction. Very important thing in quantum mechanics is for the wave function you will have to multiply, for the energy you will have to add. Very important concept in quantum mechanics. So here we have added, see, we have added to get the total energy. Here we have multiplied. For each direction we have wave function, we multiply. So very important in quantum mechanics is for the wave function you will have to multiply, for the energy you will have to add. That's the main idea. Now look at this equation, look at the wave function. We know that the wave function for the 1D will be 1 divided by root a sine pi x by a. We already studied. So here it is 3 dimension, so that's why we multiply. So this is for the x direction we have 1. Also one more thing is 1 by a to the power 3 by 2. For 1D it will be 1 by a to the power 1 by 2. For 3 dimension it will be 1 divided by a to the power 3 by 2. So that's why we written as 1 divided by root of a cube. Is it okay? So very important. Now the ground state is given as JKL. See, JKL. So quantum numbers as I said. So this is your ground state. When you are going to apply the electric field, when you are going to apply the electric field, this will go to the excited states. Correct? So it can have 3 values. One is 211, 121, 112. Degenerate levels. See, 211. So these are all excited states. This will be a ground state. We know already the electric field is along the x-axis is given by the dipole moment. The expression for dipole moment is given as mu equals Ex. We know already. We have already studied earlier in the lower class. So your perturbing field equals minus mu dot E. This also you have already studied. Dipole moment multiplied dot with dot product of electric field will give you the perturbing field. Okay. So just insert the expressions for mu and E, that will you will get this minus E, E naught x e power minus alpha t. So as I said, the transition probability using first order correction from time dependent perturbation theory is given by this expression. The square of the amplitude will give you transition probability between two states. So we can use this one. Now we can have 3 states will be there. So this will be your initial state. So we can act with this, we can act with this, and we can act with this. You have one level and there will be 3 levels, 3 degenerate levels. So your Hamiltonian, this is perturbing field, which is nothing but sandwiched between your bra and ket vectors. So this is your initial, that will be your final. So H sandwiched between bra and ket vectors. See here it is 1 1 is ground state. The first excited state is nothing but 2 1 1. Another excited state is nothing but 1 2 1. Another excited state is nothing but 1 1 2. So first we are going to consider the one by one. We are going to consider 1 1 1 2 2 1 1. Okay. You just substitute H prime, H dot perturbing field expression will be this one. We can write it. Except x, you bring all the term out. Okay, because x is the operator. So just you have an x alone. So your x sandwiched between your bra vector and ket vector. Okay, we are going to solve this one. After solving, you multiply this one, we will get the expression for or value of perturbing field. Okay. So now H prime, the perturbing field sandwiched between initial and final state is given in terms of wave mechanics as exactly like this. So you have the constant term I have pulled out. Okay, the first term, this one, first term will be 0 to 2a your x direction, 0 to 2a y direction, 0 to 2a in the z direction. So as I said, the wave function should be multiplied. So we are going to multiply. So what is this one? This must be your psi star psi. This must be your again psi star psi. This must be your psi star psi. Here it is given as You look at the first one, this is in the x direction. Okay, 1 goes to 2. So that's why you written as 2 pi x by 2a. In the y direction it is the same. 1 1 1. Here it is 2 1 1. In the y direction it is the same. See here, in the y direction it is the same. Only it varies only in the x direction. So that's why we have written the wave function is that your psi star becomes exactly like this. So this is the your wave. This is a total wave function, and we have written psi star as sine 2 pi x by 2a, and sine is nothing but psi is nothing but your sine pi x by 2a. Is it okay? So just to solve this equation, solve this integral, you will get exactly minus 32 a square by 9 pi square. Solve this integral, you will get a, and solve the last integral, you will get a. See, I repeat, it goes only towards the x direction. So that's why we have written, okay, we have written sine 2 pi x by 2a. Okay, because of the first one, 1, 2. And the answer will be, multiplying all the three, answer will be exactly like this. So we have found out the answer. What is the second one? Second excited state, from this state to this state. Okay, we can write the Perturbi field exactly like this. So you have 1 1 1, here 1 2 1. So x direction there will be no change. In the y direction there is a change. So you have to change the integral exactly like this. Psi star psi will be exactly like this. But electric field is applied only in the x direction as it is given in the problem. See, electric field is acted by the electric field in the x direction, not in the y direction, not in the z direction. So this answer will be 0 because electric field will be applied. Electric field is applied only in the x direction. So this becomes 0. Similarly, you can go for the z direction. 1 2. See, the last one will become sine 2 pi z by 2a, psi star psi. Here also psi star psi. Here also is a psi star psi. See, it means here x is here. It means psi star x psi. Okay. In the wave mechanism, you have to write exactly like this. Psi star x psi. You have to write only the expectation value. Okay. So what is the answer? Electric field is applied only in the x direction, so the answer will be 0. So you are going to add all the three. The final answer will be this one. So you have the final answer. This is your final answer. Now substitute. We will have to substitute in the transition problem. We have found out only this part alone. We have found out this part alone. Okay. So we will have to multiply with the original one. See, we will have to multiply with the original one. Okay. Original one. So which is nothing. See, we have found out only this one alone. This one alone we have found out. So we'll have to multiply with the other phase factor, which is nothing but this. So 0 to infinity, e power minus alpha t, e power I omega 2 1. 1 is initial state, 2 is a final state dt whole square. Okay, just add these two, e power minus alpha t, e power I omega 2 1 t, that will get us e power minus alpha plus I omega t. So just integrate this. Integrating will give you this. Okay, e power x, integrating, that will be e power x divided by 1. So similarly, e power 2x, integrate e power 2x divided by 2. So after integrating, you will get this. Now substitute the upper limit. Substituting the upper limit will give you 0. Substituting the lower limit, that will give you e power 0. With the lower limit, 1 minus is there. Correct? So 1 minus is there. We can write this as plus. Okay, you have 1 minus is there. So we can write this. This will become plus. This will become minus. So 1 divided by alpha minus I omega 2 1. So this is modulus squared. So we can expand into this multiplied by its own complex conjugate. Its own complex conjugate. So you will get the expression, final expression as transition probability is nothing but this expression. If you know the value, if you know this value, if you know all the values, we can find out the transition probability for this problem. So omega 21 can be written as E21 minus E1 divided by h bar. Okay. We have, there's a mistake here. Omega 21, it is not square. Okay, because we know that E equal to h bar omega, we know. So here it is omega 21, which is equal to E2 minus E1 by h bar. So that's a mistake here. Okay. Omega 21. And we know E2, the expression for E2 is nothing but, we know already, See, this is the expression for energy. Okay, so we can write this expression as E2 exactly like this. You have J square plus K square plus L square. Okay, this is for the excited state. Minus, this is for the ground state. Minus with the ground state. So 2 square plus 1 square plus 1 square. Is it okay? See here, we have 2, 1, 1. This is 1, 1, 1. So that's why written as 2 square plus 1 square plus, you get J square plus K square. You have J square plus K square plus L square. So 2 square plus 1 square plus 1 square. Simplifying, you will have 2 square is 4, 4 minus 1, that will give you 3. So we can get the value of omega 2, 1 exactly like this. Squaring will give you this expression. So if you know all the values, you can get the value of transition probability. So that is the idea. It's very important problem, and this problem may appear in your competitive examinations. Okay. So thank you, students. We will stop here.